Good evening, ladies and gentlemen, and welcome to the final presentation from the Rena and Southern Joint Branch 2020-2021 lecture season. Our lecture tonight will be on RoRo shafting dynamic measurements and will be presented by Sophie Chedziak. Before I introduce you to our speaker, I'll just run through a little bit of housekeeping. So we'll have a Q&A session at the end of the lecture. So if you wish to ask a question, you can either click the raise hand button, and then this will allow me to unmute you and turn your video on, or unmute you anyway, and you can ask your question and any follow-up questions you might have as well. Alternatively, if you do not want to be recorded, because the lecture is being recorded, you can post your question in the Q&A chat, and I will read the question out for you at the end. So to start off with, our speaker tonight, as I said, is Sophie Chedziak. Sophie graduated with an MEng in 2007 from a French graduate engineering school. Her major was mechanical engineering, and she specialised in naval architecture. She then came to the UK to work with GRC, which was then a subsidiary of Kinetic, to work on the naval architecture software Paramarine, where she carried out testing, specification development, and consultancy work. In 2013, she joined Lloyd's Register's Technical Investigation Department, and since then has been involved in various naval architecture projects such as structural assessments, stability calculations, as well as on-site shaft vibration measurement and data processing, which will be the topic of tonight's lecture. So, we invite our speaker to turn her video on, unmute herself, and share her screen.
Good evening, everyone. Can you hear me? And can you see the presentation?
We can hear you and we can see the presentation.
Good evening. So I'm Sophie, a naval architect at Lloyd's Register, as Lizzie mentioned. So I work for the Technical Investigation Department, and tonight I would like to talk about a project I worked on about 3 years ago. During the project, we installed the equipment on a new RoRo vessel to measure the shaft line dynamic behavior. We'd just like to introduce about the department I work in. Most of our work is dedicated to advisory services, which covers a wide range of field and competencies. Some of them are underlined here. It includes failure investigation, risk assessment, naval architecture analysis, ship performance assessment, and other. Tonight, I will first walk you through the overall project. I will show you the equipment installation on the shaft line, some of the post-processing steps that we carried out, and the results we got. I will talk a bit about the health and safety challenges we encountered, and finally, some overall challenges during this project. I would like to add a small disclaimer that I'm not an expert. My aim is to share a project I was involved with, and I found really exciting and interesting, so I hope you'll find it too. So let's dive in the actual project. 2 RoRo vessels were being built in China for trade in Australia and Tasmania. The ships were about 200 meters long and 30 meters wide. They are twin screw vessels fitted with 2 conventional shafts, each driving a 4-bladed controllable pitch propeller. On each shaft line, a direct drive 2-stroke engine was fitted, and there was also a shaft generator. A numerical analysis carried out by the shaft line designer suggested elevated moment and forces at the propeller hydrodynamic moment and forces. As this was a new design and the only dry dock suitable for these vessels were quite far away, any failure would have been very costly for the owners. So they decided they wanted to carry out in situ measurements to de-risk the operation of these vessels. Therefore, TID was contracted to measure the propulsion dynamic forces. They started the project and planning began to take place, which was coordinated by a TID senior engineer. We were actually contracted by the shipyard rather than the owner. And there were two sisters in the series. TID attended both vessels for static shaft line measurement, and we conducted dynamic measurement on the first ship of class. I will only present tonight the dynamic measurement aspect. As you may imagine, this was quite a complex project that required a lot of coordination and involvement of a number of colleagues. Originally, the project was won through TID Asia. We had an office in Shanghai. Two hydrodynamic specialists from TID carried out some numerical analysis and modeling. A senior engineer wrote the proposal for the on-site attendance. Another senior engineer was the overall project coordinator. The technical lead carried out most of the analysis and was also involved in the installation, led the installation. Two instrumentation specialists tested the equipment in our laboratory in Southampton, tested, prepared, and looked after the logistics. Another instrumentation specialist looked after the underwater telemetry and also at the installation of on-site of that part. Two engineers carried out some other part of the on-site installation, the data collection during the sea trials, and some of the analysis after the trials. We also had support from administration, from TID in the UK and in Asia, the finance people, some local surveyors that would help us with the shipyard, and other people that I would forget to mention, probably. Originally, so the shaft designer carried out some analysis, and TID also carried out full-scale propeller weight calculation and calculation of propeller forces. So on the left, you can see the results from the model test, the wake from the model test report. TID used a software called Procal, boundary element code for propeller analysis, and also propeller in flow software for wake scaling, and did a full-scale numerical analysis of the wake with and without assuming symmetry of the wake. The color scale is inverted between the model test report and the numerical analysis. The outcome of the TID work showed quite close correlation with the design reaction. So I'm going to show you a basic overview of the installation and then go into more detail. We installed strain gauges to assess propeller shaft bending and shear strain adjacent to the propeller flange. This would then be used to derive the propeller hydrodynamic moments and forces. The underwater telemetry was fitted under the rope guard, and the battery pack was dormant for 3 months underwater, and it was then turned on before the sea trials. Proximity transducers were built in the stern tubes, 4 at the aft end of the aft stern tube bearing, another 4 at the forward end of the aft stern tube bearing, 2 forward and 2 aft of the forward stern tube bearing, so that would 12 in total, monitoring the radial displacement of the shaft in all conditions. Inboard, we installed strain gauges to measure bending strain in the inboard spans between the bearings. We also measured the torsional shear strain and axial strain to derive torque and thrust. We measured the axial displacement at the main engine output flange. We also measured the rudder angle, the pitch of the propeller blade, the shaft RPM. TID attendances started in March 2017, and finished in October 2018. We had 4 separate attendances involving different TID staff. We ended up with 60 channels to monitor. We installed more than 600 meters of cable, which is very good for knitting. After the sea trials, we had 104 data files to analyze. This project involved quite a lot of laboratory testing beforehand to check the transmission in water and the effectiveness of the battery system for the underwater telemetry. So all this work required a lot of coordination between the different parties, TID, the surveyors in China, the shipyard and the owners. So this is a list of the channels that were being monitored. We instrumented both port and starboard shafts. The installation was identical. So on the left are the channels from the that were installed, came back to the steering gear compartment. 12 channels coming back there. And we had 24 channels on port side, 24 channels on starboard side that were all brought in National Instrument data acquisition chassis. This is a quick view of the inboard layout on one shaft. So as I said, identical on both sides. Starting from the left side, which is the aft end of the ship, we had the proximity transducer from the that were installed in the stern tubes. The wires coming back in there. We had the blade passing frequency and shaft RPM, bending strain, the B1, B3, etc. We had the thrust and torque, axial displacement at the engine. So all these channels, 24 channels, were linked to a local National Instrument chassis. And then the orange line shows the fiber optic to link it back to the data acquisition laptop. This is the layout for the whole installation. So identical port and starboard, some channels in the steering gear compartment, and they were all synchronized with each other and brought back to a data acquisition laptop located by the engine control room. I will now show you more detail the installation and some pictures taken during the installation. So the picture on the left shows the bending strain gauge installed under the between the propeller flange and the parallel part of the shaft. There were 2 sets of gauges measuring the bending strain in 2 planes 90 degrees apart, and 2 sets of gauges measuring shear strain in 2 planes 90 degrees apart as well. This is to add to get redundancy. They were all wired in a full bridge configuration. And on the right, there's the picture of all the wires coming back to a box that would be made watertight. So on the left is more a view of the radio telemetry, the battery pack and the electromagnet to power on the inductive power for the telemetry. The cable, as you can see on the right, were brought back inside by the shipyard. This installation took place about 5 months before the sea trials, and they spent 3 months underwater. The radio telemetry was mounted on a ring. It's the brownish ring on the left picture that was affixed to the back of the propeller shaft flange. The underwater telemetry was located into the steering gear compartment. The middle picture on the bottom shows one of the 4-channel telemetry. turned on in this case. The other channel in the steering gear compartment was the rudder angle. We used a draw wire, so there you can maybe barely see the draw wire just below the chain. And on the right is the installation at some point when we were testing it. And the gray box is the switch to turn on and off the inductive power to make sure we wouldn't run out of battery during the sea trials. Inside the stern tube, some eddy current proximity probes were installed. So on the left is the picture of the proximity probe without the shaft installed, and on the right you can see the proximity transducer with the shaft. At the aft end of the aft stern tube bearing, we can see on the picture two transducers. So there would be, we had the redundancy here, so we have two at 90 degrees apart to allow us to have the full radial displacement. So two pairs at the aft end and two pairs at the forward end to have redundancy, because that's one of the most important measurements during this project. Let's move on to the inboard installation. So we installed, we measured the axial strain to derive the thrust using Hilarity's configuration, which is also temperature compensated. We measured the torsional strain, and the middle picture shows you the one gauge just as it's been stuck on the shaft. We used different type of telemetry, so either Aztec or Datatel. On the left is the finished installation with the telemetry for the thrust and the torque, all tied to the shaft. On the right picture shows the one proximity probes to measure axial radial displacement at the stern tube, at the stern seal, sorry. The brackets were made by TID in advance. We also installed bending strain gauges to measure the bending strain in the inboard span between the stern tube forward bearing and the two intermediate bearings. This will allow us to estimate the running loads on the bearings. On the left, this is the picture of the axial displacement transducer installed. So we had two. One was an eddy current proximity transducer and a laser sensor. Again, the bracket was made by TID in advance. The measurement was between the flywheel and the engine. The middle picture is our project manager and senior engineer actually installing, so space is a bit limited. And the picture on the right is the reflective tape strip that we use for measuring the shaft rotational speed, and the wider strip to note where when blade A was passing, and this was linked for between all the three chassis to allow synchronization. On the right in the square yellow is the bending strain gauge installed and covered, or one of them. To measure the propeller pitch, we used the 420 milliamp current card hardwired into the local control unit. At some point, once we had to prepare for cable routing between the different compartments and back to the engine control room. So we had to go through the different watertight hatches and watertight doors, make sure we could leave them open, collaboration with the shipyard, see which one could be left open, which one couldn't, and how to make them safe enough. And despite all the preparation, corroboration, on the right picture, you can see a damaged fiber optic cable during when they closed one of the watertight doors. Luckily, that didn't stop. The cable wasn't cut through, so it was still working. Once we'd finished all of that and the ship was ready to go on sea trials, we went along. We didn't have any dedicated sea trials for our measurements. So we went along during the acceptance sea trials. There were 2 of us that would help for communication. So one of us would be in the bridge to make sure we didn't miss any opportunity to record. And one of us would be by the engine control room to check that everything was working, to start and stop the recording, and also running to the tiller flat to turning on and off the inductive power. So the different sea trials that we, during which we measured, the speed run up and run down in about 5 RPM steps. During the maneuvering, 360 degrees turning circles and various rudder angle, zigzag. We measured during the Austin trials and also during the EEDI trials. We use MATLAB and in-house script to carry out the post-processing. We mostly worked out the mean values of the different values that we get and the vibratory components. We compared with predictions and also against any standards or any limiting values that we know of. We looked at the order analysis and at the shaft orbit plots. I will show you some results only for the run-ups, but the principle is the same for all the different trials that we analyzed. So first of all, one of the most important thing was the propeller hydrodynamic moment and forces. So this is an example of the results at the port propeller, the vertical plane moment. So we had, as I said, we had redundancy. So the thick lines shows good correlation between the 2 measurements at the same location, which is good. In the thinner line show the maximum and minimum during each run. And we compared these values, experimental values, against the numerical values that both TID had calculated and the shaft designer. We also look at the vibratory aspect. So this is a waterfall plot for the bending strain. And we could see, so it's a 4-blade, it was a 4-blade propeller. So you can see the 3rd and 5th order as the blade rate vibration is modulated by the shaft rotation rate. And it's useful to check if there is any resonance or force vibration. From the bending strain measurements in the inboard spans between each bearing, we can work out the bearing loads, bearing reaction force. So the measured value along with the model that we make with our software, with our MASAC, it's called MASAC software, we can work out the bearing reaction. We assume a single point of support, and we can also derive the maximum nominal pressure due to the loading. And we check that against load register limits. So in this case, it was all within the limits. From the various proximity transducer installed in the stern tube, aft stern tube bearing and forward stern tube bearing, we can work out the orbit plot and the displacement of the shaft. So on the left is the radial displacement at the aft end of the aft stern tube bearing. Again, we had redundancy built in, so the blue and red lines show good correlation. We can also see that it didn't go into the bearing, the clearance, which is the red circle. On the right is the waterfall plot for a similar measurement. The first shaft order is due to a run out or slight imbalance of the shaft. And we could work out that the radial displacement of the port and starboard propeller shafts were satisfactory. So the previous picture showed the mean values, and we also looked at the maximum single amplitude values for all the sensors. We derived the thrust in the shaft. This is quite a difficult measurement. The strain due to the thrust is quite small, is very small compared to the noise and other strains. We got the mean values and the vibratory components. In this case, the curves do not follow the typical quadratic form, as the shipyard was not using the combinator curve, but was manually changing the pitch as they were increasing the shaft RPM. From the torsional strain, we calculated the shaft power. This is useful to compare against reading from the ship system, for instance. So that's the mean value of the shaft power during the run-up trials, both port and starboard shaft. During the run-ups, we also analyzed the vibration component. So this is the torque, the waterfall plot for the torque, the shaft torque. And we can see a peak at a frequency of about 4.1 Hertz, which is likely to be a resonance of the first mode natural frequency of the shaft. And on the next line, we can calculate the torsional shear stress and compare it against load register limit for continuous operation. So the limit is the dotted line, and the calculated values from our measurements are the red and green lines. So on the left, you can see that it's going above the limit, which is the peak that we saw on the waterfall plot before. That confirms the design bar speed range of about between 22 and 32 RPM. The conclusion from the measurements was that there were no elevated bearing load in operation. The propeller shaft radial displacement was not exceeding any restriction. There were no undue vibration, and we confirmed the design bar speed range. All during the run-up, the run-down, and during the different maneuvers. So next, I will go on and show you some health and safety hazards that we encountered during our project. So on the left is the ladder, stairs that were installed to get off the ship. So I came up a bit of as a surprise. So I had to be careful when carrying things up and down. On the right is when I picked up an extension lead to plug some of our equipment. Needless to say that we didn't do this installation and dodgy wiring. On the left is a picture of the radar on the bridge during the sea trials. Radar and AIS laid over it. So it's quite a busy area just before starting the sea trials. Going back to the picture of my colleague installing the Axial displacement transducer. To make sure that that was safe, we isolated the air start valve of the engine with bike locks. Some challenges and lessons that we've learned, or I certainly learned from this this project. As I mentioned, we were contracted by the shipyard, but it's the owner that required these measurements to be taken. So we were kind of the ship was still in construction at the end of the construction, where it's quite busy for the shipyard, so they didn't always want us there. We were interfering with their work. There was a lot of concurrent work between us and the shipyard. We had some issues that they wouldn't plug some of our electrical equipment would be unplugged whilst we were working. Coming back after one attendance, we found out that our equipment had been pressure washed. Luckily, that didn't affect the installation. We experienced a blackout during the installation, which is always helpful. So to mitigate and to help try and work better, we sometimes work at night where it will be quieter. Some of the channels, especially in the transducers, the proximity probes in the stern tube bearing didn't work when we came back. So we don't really know why. Maybe some wires were damaged when the shaft was installed, which is a good thing that we had the redundancy, so we didn't lose out in the end. The under telemetry worked really well. The battery life was enough, and the electromagnet and the switch on and off worked all the time during the sea trial, so that was a really good thing. Communication was sometimes difficult. There was the language barrier that doesn't help, and because they were not dedicated trials but acceptance trials, the shipyard was the employees were really busy, so we had to fit in and not disturb them. So having two people was really helpful, so we could make sure that one of us was always up and making sure that we didn't miss any opportunity to record data. The underwater telemetry worked really well. The good preparation and testing and logistic paid off. More about the preparation. Again, all the bracketing, the machining beforehand was really helpful. So when we came on board, we could just install the brackets and it was working. So as a whole, I think it was a successful project. I found it really challenging and interesting. I would like to thank all my colleagues and all the people that made it possible, that taught me a lot. I definitely learned a lot on this project, and I wish I could do it more often. So thank you to everyone, and thank you to you listening. See if you have any questions, I'd be happy to answer.
Thank you, Sophie, for a very interesting talk. We currently have one question at the moment, but I hope other people will post questions as well. So this question is, can you put a ballpark figure for the cost of the shipbuilder for this exercise?
The cost to the shipbuilder, our installation and all our work was, our contract was with the shipyard, but in the end, the owner was paying for it. So for the, sorry, the question was the cost for the shipyard or for the ship owner? I
think the basic question is, how much did the whole thing really cost?
I don't know. I think looking back at the project, we spent, I want to say about 600 hours, I think. I don't know. I was not really involved in the finance aspect, but it was several weeks of work and the logistic and buying some equipment, because the underwater telemetry, we had to purchase some equipment for it. So certainly it's a big project.
that sounds like in the hundreds of thousands, not the tens of thousands. Let's put it this way. Doesn't seem to be anyone else wanting to ask a question at the moment. We have another question. How did the results align with the design?
We there were, I have the paper here. Where is it? So we had difference between port and starboard. They were in the same ballpark figure, but we had smaller forces on one side and slightly bigger on the other side. So, but it was in the same order of magnitude.
All right. So
the design.
So the hydrodynamic predictions were pretty reasonable then.
Yes. Yeah.
Okay. Doesn't seem to be any other questions. So, once again, thank you for your lecture.
Thank you for the opportunity.
As I said at the start of the lecture, this is the last one of the 2020-2021 season. We will be on our summer holidays. We will be back in October on the 6th, I believe, and I think the lecture will be on brittle fracture and steel ships. We will be announcing our lecture program this month, I hope, in our bulletin, the Shipping Lanes, which is a quarterly bulletin you should all receive via email. So you'll be able to put the dates in your calendars. And then we will announce each lecture in turn in terms of like invites and things about a month before, like we have been normally. We are going to experiment over the summer with hybrid lectures. So it may be in person and on Zoom. We're not sure yet whether we can't confirm that yet, but we are going to attempt to do that because the Zoom lectures format has been working well. And certainly people have been quite positive about, well, not having to travel, I suppose, after work to be able to watch lectures. But equally, I know some of you want to get back to in-person lectures. As usual, the lecture has been recorded and will be uploaded to YouTube next week. And so will be available then. And I guess someone else has thanked you for sharing the project and has appreciates getting the knowledge. So we have some positive feedback for you, Sophie.
Thank you.
Yeah. And then another question has actually come. I think you might have mentioned this at the start, but someone's asked, why did the owner require the investigation?
Some calculation had been done by the shaft designer, and they were showing slightly elevated forces and moments. And it's mostly because the ship were bigger than any ships they had, and there was no dry dock available next to it. So they meant to trade in Australia, and the dry dock they would use would be in Singapore. So any failure, would require weeks of unavailability of the ship. So they decided that it was worth doing these measurements to de-risk the ships. And also they were new designs, so there was no experience, no practical experience of how they would behave. So it's basically to de-risk the operation of the ship.
Okay, thank you. Doesn't seem to be any others. So I guess I will wish you all a good evening and hope you have a good summer and that the government releases us from lockdown, final lockdown measures. And I hope to see you all in October. So good night.
Thank you. Good night, everyone.